right.
Like a scientist, like a scale of super K.
So I'm going to go ahead and get started, even though nobody's here.
I noticed that.
Okay. So today I'm going to start off with a bunch of graphics that I want to show you guys, discussing turbulence and what it is and what it means. So this is one of the big questions that I got was, what does turbulence in outer space look like? Is there a good way to do that? No. Just all dark or no dark. So this is the Carina Nebula. How many of you have seen this image? So this is the Carina Nebula, and it's a molecular cloud, and this is I thought I had a higher resolution. This is the most 8-bit looking version that I've ever seen. So this is the Carina Nebula, and we can compute what the flow is doing in here. We can measure it, because we can measure the velocity of this cloud, and we make the power spectrum of the kinetic energy in the cloud, and we can see that this has a power law in the velocity. More importantly, you can compute the Reynolds number of this. So there's this big OB association. So that's a collection of O stars and B stars that are right here. You can see them because of the James Webb diffraction spikes. And those stars are lighting up this cloud and driving turbulence in the cloud. And you can compute the Reynolds number of that, and the Reynolds number is like 10 to the 14. You get some really ridiculous numbers. So it has to be turbulent. And the best measurement, and one of the earliest measurements that I know of that actually demonstrated that outer space is turbulent is this paper from Armstrong, Spangler, and Rickett, or Armstrong, Rickett, and Spangler. And this guy, the second author, was on my thesis committee. I only met him twice, but he was super into what I was doing, so that was cool. And I'm into what he's doing. So what this is a bunch of measurements of what's called radio scintillation. And that means you take a big radio telescope and you park on a star and you watch it in time for the star to wiggle. And it wiggles because of Snell's law, so the varying diffraction of the plasma. Oh, hey, there's everybody. So I'll just vamp for a second while you guys sit down. So basically, what I'm putting up is a plot of turbulence in outer space. So they take a radio telescope and they park it on some stars, and they watch the stars wiggle back and forth, just like watching the twinkling of stars. If you've ever gone out and watched stars and seen them twinkle, this is the same twinkle or a similar twinkle, but instead of being due to the atmosphere, it's due to the gas in interstellar space. And what is measured is this is the power of the density fluctuations. So what does that mean? So you take the density, you take a density field, or the density as a function of time. This is a time series. So you take the density as a function of time, and you take its Fourier transform, and you square that. And then you get the power spectrum. So it's not a particularly complicated thing to get. You just take a quantity, you take its Fourier transform, and you square it, and you get this power spectrum, which shows that we have large fluctuations. And so this is how much power in the density fluctuations versus wave number. So this is K. So this is big scales over here and small scales over here. And you can see this really gorgeous power law that is covered by all kinds of different things. So these are rotation measured fluctuations. So they're very, very large scale structures. So this is about 1 million meters, or this is about 1 million meters, and this is about 100 light years. So this is these are very large structures, and these are structures that are kind of like the size of granules on the sun. So But these are interstellar fluctuations. So they do all of these with various kinds of radio scintillation. So that's what turbulence looks like in outer space, and that's how we measure it in outer space, and that's how we can say, hey, this looks like this cloud is actually properly turbulent. The other thing I wanted to show you is my father-in-law's pool. Which one goes first? This one goes first. So the reason I wanted to put this up is to talk about correlation functions. So where's my pointer? Here. So what's going on here? Oh, it's so noisy. Oh, I can't turn the volume off. How do I mute? I really don't care about listening to it. So what we're seeing is my, I had to go find these images, and I took these movies in 2019, so I had to scroll through all my pandemic pictures. It was depressing. But anyway, so what's going on here is we're at my father-in-law's pool, and he just lives up the street from me, which is great. And my kid is kicking his feet in the water down here. And this projector is kind of terrible, but what you can see is that you've got a whole lot of tight little fluctuations here, right near where he's kicking. And then the fluctuations kind of die out, and you get this much smoother flow out here. And so this is a visualization of what the correlation function means. So he's kicking his feet here, and let's actually, did he stop? I think he stopped. Because, so you can see, and if the whole thing were turbulent, this would still be true, but here we just have one source of turbulence. And so you can see that real close to his feet, it's real chaotic. So if I have an idea of what's going on here, that's going to predict what's going on close to his feet, because you know it's going to be chaotic. And that correlation falls off as you go further away. And out here, we have a much longer correlation length. You can tell because it's a lot smoother. The correlation length out here is long, whereas the correlation down here, because the fluctuations are all short and tight, is very small. So I have a couple kind of 1D plots. I'm always losing my mouse on this thing.
You can see it on the screen, but not probably on.
Yeah, I can see on that screen. I'm not sure why it's not showing up in OBS anymore. They used to. So if we take a random signal, so here are two different random signals. And what's plotted are three different things. So these are two different random signals. So this is my signal here, and this is my signal here. So what can you say is different about this signal versus this signal?
The bottom one is noisier.
It looks noisier, yeah. Anything else that anybody?
The top one has like one big fluctuation. Like
Yeah.
It's like a big splash compared to like little tiny.
Right. This one has a big bump, and then these other bigger bumps. Like it's got a structure. Like there are these bigger structures here, whereas you don't get any really big structures here. They're all small fluctuations. So these are two different correlation functions. So the noise, and here, because I'm just looking at a single plot, I'm just looking at the correlation function averaged. So this is the correlation function, which is, this is some quantity q, and let's call this t. It could be space, it doesn't really matter, because the correlation function is the same idea. It's q of t times q of t plus some difference, and then you average over all the time, and you get this quantity that looks like this. It kind of falls off, and then it picks back up again. So you got to ignore this second half, because it picks back up again because it's periodic. the signal's periodic. Why did I make a periodic signal? Because I'm going to take a Fourier transform of it. And when you shove something into a Fourier transform, the Fourier transform assumes that it's periodic, because that's how they work. So this signal's periodic, it's the same, but that's just for convenience. So here you can see the correlation function is kind of long and falls off to 0 at some distance. Whereas this one, the correlation function is 1 at 0 lag, and then basically 0 anywhere else. This is a signal that we would call delta correlated, because the correlation function is a delta function. It's only non-zero at the origin, so only things that are immediately next to each other in space or time have any relationship. And as soon as you're away from that original point, you have no idea what's going on. Whereas with this signal, you have some correlation length. So if I've got a point up here, I know that I'm going to be close to up here. I'm not going to jump way down to -2, even though that's allowed by the random number generator. You know that because there's some correlation length, I got to go way over here before I have a value that's very different from the value that I have at one point. Does that make sense? At least a little bit. Let's see, is there anything else that I got? No, that's all I had to say. Does anybody have any questions about that? It's just, yeah.
What kind of fluid would be delta correlated?
All of them, if that's the model that you're using. So it's not a great model, but you can do math with it, so it gets used. Some things are delta correlated. So a fluid's not going to be delta correlated because you've got viscous terms that are going to it's always going to have some correlation length in a fluid. But you can have other things like shot noise in an electrical circuit, and that is going to be delta correlated because that's just random electrons, and every electron is its own thing. So the random crap you get now is going to be different from the random crap you get even a millisecond later because the electrons are all gone. So, so some things are delta correlated, but fluids tend to not be. But this is a tool that's useful for all kinds of things, and this is one of the things that gets fed into like machine learning and clustering algorithms, is looking for properties of your fluid flow or your random variable that do that. Okay, so now I'm going to talk about. Oh, actually, the first thing I'm going to do is write down what I'm going to do so that I stay on task instead of jumping around like a squirrel. So I'm going to show you some pictures that exemplify some of these things. Now I'm going to do Richards diffusion. I'm going to quick recap. The only derivation I'm going to do again is the Richards diffusion because that one is not in the book. And I'll explain what it is and why I care about it and where it fits into two potatoes drifting apart in the ocean. So that's really our kind of cartoon model. It's two potatoes drifting apart in the ocean. How fast do they drift apart and when? Because as they drift apart, they're going to sample different parts of the turbulent cascade. And when they're very close together, they're going to move basically ballistically. And as they get pulled apart, then they're going to enter the turbulent cascade and they'll get pulled apart fast. And then once they're much more separated than the turbulent cascade, then they're just going to wander around more like a random walk again. But a random walk that's driven by the turbulence. So the one in the middle is Richards diffusion, and that's the superballistic diffusion that actually gets you mixing. So I'll recap that. And then I'll talk about moments of distributions, which seems like I'm jumping completely off topic, but I'm not. If I've got some distribution and I know all its moments, that's good enough. That's basically like knowing the distribution. And what I'm going to show you is that you can't do that for the hydrodynamics equations. So Navier-Stokes doesn't let you take more moments because it just gives you the finger. So then we'll do the Reynolds stress. And this is cool because it's an active area of research, so there's funding to be had for understanding turbulence and the Reynolds stress. But it also shows us the end of human knowledge. So one of the things that I like about the Navier-Stokes equation is you can derive it from first principles, and we did, and you will, and you have, just by saying, okay, this is how physics should work. Here is math. And then you can take that math to the end of what human beings can do, because I can show you that we can't actually complete the solution space to this equation. So that's an open area of research that'll get you famous if you can solve that problem. I'm not suggesting that. It'll drive you crazy. So we'll talk about the Reynolds stresses, and then we'll talk about how to fix the Reynolds stress, because it is a problem when you're trying to model a flow. And then we'll talk about mixing length. And then we'll talk a little bit about DNS and LES, which is direct numerical simulation and large eddy simulations. And I'll talk about those in a minute. But, oh, and then if I have a minute, I'm going to show you the only analytic result that comes out of turbulence. There's only one thing that you can actually write down and say, it has to be 4/5. Everywhere else is, it's a constant of order 1, we hope. Yeah?
This might be kind of unrelated, but does fire work the same way as turbulent fluids?
Fire behaves
Explain.
with an advection diffusion equation. So it doesn't develop turbulence in the same way, but it does get chaotic because of the advection part. But it is tightly coupled to turbulence, so turbulence is, and that's actually a great model. So so I'll talk about how this would impact fire, because that's an interesting question. Okay, so Richard's diffusion, let's do that real quick again. I want to do that first because it's on the homework, so I want to make sure that it's at the beginning of the video, because it's the bit that isn't in the book. Okay, so, let's turn that off. Turning off. So, let's start by doing it totally wrong. Let's start by not doing it wrong. So, V equals epsilon L to the 1/3. This is kind of the key relationship in a turbulent fluid, is that the velocity difference between 2 points is going to go like their separation to this positive power. It's not bigger than 1, but it's bigger than 0. And why is this? This is because we assume that the energy dissipation rate has got to be v squared over a time, and the time has got to be the length over the velocity. So the dissipation rate is v cubed over a length. So the velocity equals epsilon L all to the 1/3 times some constant, which we don't know what that constant is. So this is the derivation for the turbulent cascade. Make sure that makes sense. Yeah.
So the epsilon is also to the 1/3?
Yes, this is v to the 1/3. And then there's a constant here in front, but we're just going to absorb all of these in a magical constant that I'm just going to keep in my head. Right? There's a proportionality in here that's like order 1, but it doesn't depend on length. It doesn't depend on anything else. I'll just put it back in at the end. So v goes like L to the 1/3. dl dt then goes like L to the 1/3. And what we want to find is d by dt of L squared. So I multiply by an L, and I get 1/2 dl squared dt equals L to the 2/3. Oh no, sorry, that's not how that works. I'm not squaring it. I'm not squaring this, I'm adding 1, L to the 4/3, because that's L to the 1/3 plus L, right? So I multiply L by both sides, and then I just absorb my L into here using product rule, and my L becomes 4/3. So now let's treat this other quantity, we'll call it Q, which is L squared. L squared is the quantity that I'm interested in. So we're going to rewrite this as dq dt equals Q to the 2/3. So this comes over here, and you get Q to the minus 2/3 dq equals dt. And then I integrate this, and this goes up by a power, so this becomes Q to the 1/3 equals t, or L to the 2, or L squared goes like t cubed. Everybody follow that? You just multiply by L and then integrate. And this gives us that L squared goes like t cubed, and this is the superballistic motion. So in our, as you've got a turbulent fluid, you have several length scales to deal with. So if the length is way less than the dissipation length, then you have molecular diffusion, and average x squared is going to go like the molecular diffusion constant times t. If you're at the bottom of the cascade, near the dissipation length, then average x squared goes like t squared, and you get basically ballistic motion, and the material's just pushed around because they're kind of close to each other. When L is in the inertial range, then average x squared goes like t cubed, because you have this v goes like L to the 1/3. So the further you get apart, the bigger the velocity difference. So you get carried apart much faster than you would just by random walk. And then 4, when the length is larger than the outer scale of the turbulence, so this is the driving scale, then again you get x squared now goes like the turbulent diffusion constant times t again. It becomes more like turbulent diffusion. Now, nature has some smooth way of actually doing this, and we don't understand. But when you break it up into chunks like this, then you get this hierarchy of diffusion timescales. Does anybody have any questions about this or that?
Can you explain again what dm and dt are?
Yeah, dm is the molecular diffusion coefficient, and you get that from the mean free path and some other stuff, and I'm not really worried about that. That comes from the molecules banging into each other. And dt is like v squared times the correlation length or something like that. What are the units got to be? But the units have got to be right, so I'm just going to put big quotes around that. So dt is the turbulent diffusion, and this comes from the correlation function of the turbulence. But it's just a number that you compute. The behavior with t is the important part. So it's just some number times t, and this is just some number times t. And this is the molecular diffusion coefficient, and this is the turbulent diffusion coefficient, and they're different. And there should be coefficients in front of the other two as well. I'm just interested in the behavior with time at this moment. Okay, so now, now I'm changing gears, and then I'll be on the same gear. So if I have a probability distribution, which I've asked this before, how many of you have taken a stats class? Not many, a couple, a little bit. Okay. So a probability distribution is how you describe a random process. So, and this is true in general for a lot of things. So I have some probability distributions of some quantity Q, whatever that is. This could be, you know, the number of cheeseburgers eaten by video game players or whatever. So you have some distribution. And I know that the norm, the integral of P dq is equal to what?
Oh.
1.
Yeah, exactly. 1, that's got to be 1. All the probabilities, you just add up all the probabilities and you get 1. The average, which we'll call the average of x, average of q, is q, p of q, dq, and this is the average of q. So this tells us where most of the stuff is. So average of q is like here. And the average of q and the peak of the distribution are often not at the same spot. Also, the average of q can always be reset to 0 by just subtracting q from everything, by just subtracting q from everything. So this is probably 0. The variance, q squared, is the integral of q squared, p of q dq. And that tells you about the width of the distribution. I'm going to keep going. Let's get q cubed, which is just the integral of q cubed, p of q dq. And this tells you about how lopsided it is. If it slants like this, or if it slants like this. And then you can get, and this is called the skewness. Actually, the skewness is this divided by the square, by the second moment, but it doesn't matter. So this gives you the shape. And then you can get the fourth moment, and it gives you how flat it is at the top, and the shape. So you keep going on and on and on and on and on, and if I have all of the moments of my distribution, I effectively have that distribution. I know all of the information that there is to know about this distribution. Does that make sense? More or less. So we're going to try to do this, but for the Navier-Stokes equation, and we're going to fall on our face. And I'll show you where that is, and I'll show you what we do to take care of it. So let's start with the Reynolds stress. So like what we did when we linearized things, we're going to break the flow V, actually let's call it Q again, just because we're being generic. Q is going to equal Q bar, which is the average of the flow, over some averaging kernel. So typically this is, formally this is an ensemble average, so we do the same experiment 500 times and average the result. Plus Q prime, which is the fluctuation around that average. So if I average Q, if I just take Q bar, this is going to be equal to Q bar bar plus Q prime bar. And clearly that has to equal Q bar because it's Q bar. So this one has to be 0. If I average the fluctuating part, it goes away. That's the only tool I've got right now. And if I average the average, I just get the average, right? Because it's a constant. It's just one number. So once I've done the integral, I can't do the integral over that number again because there's no free variables anymore. So what we're going to do is we're going to do this for all of my variables. I'm going to plug it into Navier-Stokes. We're going to expand it. And then here, if we're allowed to, and Q prime is small, then we can throw out all the things with 2 Q primes on it. but it's not. So we have to keep them all. And it gets worse, and then it gets better, but not a lot better. And then I'll show you why it gets worse again. So let's just do it. So dv dt equals plus d, okay, let's call this rho v. We'll do this with the momentum equation rather than Navier-Stokes, but it's very similar. But it makes life a little easier. As d by di of rho vi vj plus p delta ij plus d by dgi, sorry, that's a j, vi. So this should be familiar so far, equals 0. So this is my v dot grad v term in Navier-Stokes. This is my pressure term, and this is my del squared, oh, there I need a nu. Plus nu times del squared v. The other part of the del is here. So is this good? Everybody happy about it? So I'm just going to plug in my primes and my unprimes, and I'm going to, I'll just do it once. So I get d by dt of rho, and here rho is constant, so we don't need to expand the density. This is all incompressible. It's just so much worse to do it with compressible that nobody ever does. So this is rho vi bar plus vi prime plus d by dj of rho vi bar plus vi prime times vj bar plus vj prime plus p bar plus p prime delta ij plus nu d by dj of vi bar plus vi prime. Still equals 0. Okay, all I did was stick this into here, and it gets a little bigger. And it's kind of bad. This is this is a true equation. This is factual. That's true as Navier-Stokes is, and Navier-Stokes works pretty great. So let's expand all of this. So I've got a d by dj of rho vi bar vj bar plus vi bar vj prime plus vi prime vj bar plus vi prime vj prime plus the pressure and the viscosity. Those are the same, but I want to talk about these for a second. So I've expanded this. Then I average what I've got, because I mean, this is for a snapshot in time, which isn't that useful. If I've got a wind tunnel, I'm going to be making averages, but however I'm measuring it is going to be averaging in some way. I want to be able to talk about the average. So we take this equation and we average all the terms. So let's look at each one of these terms by one by itself. So this term, when I average vi bar vj bar, the average of that is just vi bar vj bar, because they're just numbers. We did the average. You can't average it again. You get the same thing. The second term, vi bar vj prime, when I average that, what's that?
0?
Yes, why?
Because the average of the prime is 0.
Yeah, and the average comes out of the average, because it's just a number. And then you're just left with the average of the v prime term, which is 0. Sweet. Then we have the v prime I vj bar term. We average that. We get 0 for the same reason. And then we get the VI prime VJ prime bar. What can I say about that? Nothing. Because it doesn't go away by itself, and it's a thing that we got to deal with. And then for the fluctuating pressure, the P prime goes away, and for the dissipation term, the V prime goes away. And we're left with, and in this term, this goes away. So let me just highlight the things that go away. So this goes away, this goes away, this goes away, this goes away, and this goes away. So go back and collect all our terms. I'm left with d by dt of rho vi bar plus d by dj of rho vi bar vj bar plus p bar delta I j plus nu dj vi bar. This is just Navier-Stokes equation with the barred terms, but I'm not done. And that's the part that sucks. Because now once I've done this process, I'm also left with a rho vi prime vj prime bar. Okay, is everybody with me so far with what I did? Yeah.
So that term doesn't go away for the same reason that like the average value of the velocity is like 0, but the average value of like the velocity squared would not be a 0. So
That's
it's the same
exactly
idea.
right. That's exactly right. Exactly. Did everybody follow what he just said? So the mean of x in my random process, my mean displacement is 0. But my mean squared displacement is actually how far away from the origin I do go. Even though I'm just orbiting the origin, the mean squared is not 0 because it's a square term. Because you got two quantities. So this is a pathology of the Navier-Stokes equation, and it's really because of this v dot grad v term. It's because I've got two velocities here, which really doesn't seem like it's all that much. I have two of them. One of them is really easy. I can do that. We know how to solve. If it's linear, I can solve anything that's linear. I just call it a Fourier transform, and all my time derivatives go to omegas. I'm done. Yeah.
Could you explain why the primes go away in that step, like in third? Like when you first start right there, yeah.
Here?
Yeah, why do the primes?
So I'm averaging both sides. So I do an average over everything. And when I average the fluctuating term, I get nothing because it's deviations from the average. Does that make sense? So that's why we don't have any primes except for this guy. So now, why is this a problem? Well, because when this is just one example of why this is hard. When I'm doing hydrodynamics in the computer, I break space into a set of boxes. And usually I use more like 100 million of them, but that's really hard to draw. So we'll go with 16. So one of these boxes, I'm going to call this QI, where Q is now density, velocity, energy, also magnetic fields and chemical composition, whatever. QI is equal to the average of Q of x, y, z. This is the real value that I know over zone I. So I have some real solution in here. And what I have in this box is just the average over whatever the real solution is in the box. Does that make sense? So I'm just kind of quantizing space and then doing hydrodynamics on that, which works great, except for I know that this term is not incorporated in that. So the process of calling this an average and then writing down a Navier-Stokes equation for it is kind of wrong because we're skipping this term. Now there's ways around that, and we'll talk about that in a second, but this is kind of a headache. So let's get an expression for VI, VJ. Let's try to do that. And I'm not actually going to get very far before I show you that it's all going to fail. So d by dt of rho vi prime vj prime bar. How do I get at what this is? So just like we've done several times in the homeworks when I've asked you to derive like the momentum equation or the internal energy equation, start with the thing that you are looking for, expand it out with product rule, plug in the stuff that you know, see what you got.
Shouldn't that
So-
be delta J?
What's that?
Shouldn't you be taking, isn't that the derivative with respect to?
No, this is the derivative with respect to time. So this shows up in a dj, right? But I need to know how this evolves.
Oh,
So we're going to write a new equation that is the time derivative of this. So this is a new equation that we're going to try to get. Because now I have some other quantity. Like this, I've got some other quantity, we'll call it capital Q, which is rho vi prime vj prime bar. I've got this other quantity, so now I need to know what dq dt is. So this is equal to rho times vj prime d by dt of vi prime bar. Oh, why do I get to bring the derivative inside the average? I have this recurring cramp in my side, and it wakes me up in the middle of the night, and it's suddenly Charlie voicing right now. It's penance for not doing yoga enough. So why am I allowed to bring this time, this is an average, why am I allowed to bring the time derivative inside? Because this is an integral, right? This is an integral over ensemble of vi prime vj prime, and I'm taking the time derivative of that. My derivative is a linear operator, and my integral is a linear operator, so they commute. Linear operators tend to commute. But more importantly, there's a basic theorem that derivatives and integrals commute. So I'm allowed to do this, and then I got plus rho vi prime d by dt of vj prime bar of that. Okay, so these two terms look the same, but one's for I and one's for j. Okay, now let's see what that is. So that is equal to, let's expand that out. That's equal to minus rho v j prime d by d k. I got to introduce a new variable here because this is a different dot product. D by dk of rho vi prime vk prime, and all of this is average. So you can see I'm going to integrate this by parts and bring this vj in here, and I'm going to have a term that looks like rho times d by dk of this new horrible thing, vi prime vj prime vk prime, and the average of that. And I'm not going to write anything else because I don't know how to make this. I couldn't find it for 2. I sure as hell can't find it for 3. If I try to write down an evolution for this, I get a term that depends on the 4th moment. I get another one. And if I try to write down an evolution equation for that, it depends on the 5th. So you have this hierarchy problem of you're not able to just take a bunch of averages, which is what we do as physicists. We just take a bunch of averages and see what we get and try and hope that things simplify. But this doesn't work here. So as the human race, our math skills come up short now. We don't have techniques for actually solving this. Yeah.
I just don't get what these two terms are, like where you,
Oh, yeah, I was gonna ask the same
yeah,
thing.
like I don't get where you brought these in from.
Where I got this?
No,
No,
how
no, like
you-
the two terms,
yeah.
yeah, these two terms.
Okay, so d by dt of vi prime. Let's write an equation for that. That's just going to be d by dt times vi prime, vj prime, and then these will all get primes on them, right? So this is my equation for this guy. It's inside this term and it's multiplied by vj. Does that make sense? So I'm just plugging in this into here, which just gives me this. And there's a pressure and another term, but I'm skipping that. So let's just think about what this term does. Does that make sense?
So you're pulling it from not being steps.
Yeah, so I'm just, so here, I could use Navier-Stokes again. So I can just solve for the, so I know that d by dt of rho vi prime equals minus d by dj, and let's call it, not use j because I'm already using j, d by dk of rho vi prime vk prime plus the pressure term plus the diffusion term. But those don't matter, those aren't problems. So I just plug in this, so I'm just going to wave my hands past those because I don't care about them. Let's worry about this term. So when I plug this term in, then I'm left with rho vj times d by dk of rho vi vk, which is just this term over here. Does that make sense? So we're just taking Navier-Stokes and cramming it in there, whether or not it fits. And what comes out is a term that looks like this. And so if I'm going to try to find an evolution equation for this, I'm going to get a worse equation, and then a worse equation, and then a worse equation. So we have to stop trying to get more equations. So we stop here. This term is called the Reynolds stress. One of the homework questions is simply derive the Reynolds stress. So what I want you to do is just go through the things that I did. Not this part, just the first part where we wind up with this extra term that's a problem. So what does this term mean? Let's talk about that for a second. When I got d by dj of rho vi prime vj prime bar. This, I'm just going to rewrite this as rho vj prime d by dj vi prime bar plus rho vi d by dj of vj bar prime. So we can interpret this as the interaction of little fluctuations pushing around other little fluctuations. Does that make sense? So when I write down Navier-Stokes, I get d by dt of v equals minus v dot grad v plus the pressure term. This term is the velocity pushing around the velocity. Let's talk about that for a second. So if I have instead just scalar advection, so not for a velocity, just for some contaminant, I can write down dq dt equals minus c times dq dx. So this term is fluctuations in q being pushed around by my velocity c. So this is just, I've got some stuff and it advects to the left with some velocity c. That's how you would write this. That's what this equation says. And so what that means is a fluctuation in q, the stuff on the inside of the gradient is what's getting pushed around. And the stuff on the outside of the gradient is what's doing the pushing. Does that make sense? So if you remember when we solved this, we found that the initial conditions are static, they just go forward in time. So whatever my solution to this equation is just q of x and t equals q of x naught and t naught by way of x minus ct. So q of x and t equals q of x minus ct, which is just equal to the initial conditions translated by some amount. So that's something that we've done a couple of times before. So when I look at v dot grad something, we can interpret this as the thing outside pushing around the thing inside. So this term is the interaction of little fluctuations with little fluctuations. And they might not be little fluctuations. They might actually be substantial fluctuations. They might be the entire flow. So what do we do with that? So let's talk about how we fake it. So I've got this term, I've got this Reynolds stress. So the important takeaways for what I want you to be able to do is to derive this and understand where this comes from, and to interpret what this term is telling you, as this is the interaction of fluctuations interacting with fluctuations. So we threw out, when we were in the process of our derivation, we had a term that went VI bar times Vj prime. This term is fluctuations being pushed around by the mean flow. And that one, that's easy to deal with because they just get moved around. That's fine. That one disappears when we average it. I'm not going to want you to take extra moments. I just wanted to show you that to say, hey, this is the end. This is the end of our knowledge of this equation. We can't dig deeper without going somewhere else. This equation has told us what it can tell us. So how do we deal with this? So what we deal with, so the first order line of defense is called mixing length. So, turbulence diffusion, Reynolds stress, get my stuff. So this is where we start waving our hands enough to fly, because the equations have forsaken us, or human understanding has forsaken us. Either, it's hard to say. There might exist some way to close these equations that we haven't discovered yet, but I think that's probably not right. I don't think that's true. So we go with this thing called mixing length theory. And mixing length theory was really developed for convection zones in stars. That's one of the big places where it was developed. So in a star, you have some core that's hot, that's making things hot. And because it's hot, you're going to have some region that's turbulent. That was a lion. Roar. You have some region that's turbulent. And so what we want to do is we want to say, okay, the turbulence, it only happens over some length. We're calling it the mixing length. And now we're going to look at how the diffusion term looks. So my diffusion term is nu times d by dj of Vi. So my diffusion, now you can also call this nu squared if I'm thinking about inside here. So if you remember how we ballparked the viscosity, when I just made up a viscosity, when I said, okay, I need to pull a viscosity out of air, I just need to ballpark what the viscosity is. The viscosity is equal to the mean free path of the particle, so that's how far a particle is going to randomly go, times its RMS velocity. And we have expressions for both of these. The mean free path goes like 1 over the number density times the cross section of the particle, and the thermal velocity goes like the square root of kT. So we can ballpark this. The important thing is that the viscosity, how we're dissipating the turbulence, how we're moving turbulence around, how we're moving stuff around, goes like some length scale times some velocity scale. And we're going to plug in some length scales times some velocity gradients. So we're going to say that I've got some length, and I'm going to say that Vi prime Vj prime bar, the Reynolds stress, is going to equal, is going to equal some mixing viscosity times dV bar dx. So it's some viscosity times some gradient in the velocity. Because the gradients in the velocity are really what matter. So this is the first approximation. And this is, open up thin air and pulling it out. Units wise, it has to work like this. But, so we're just going to model it this way. But the important thing is, the fluctuating quantities aren't something that I can measure. I can't measure the fluctuating quantities. Because remember how this works. I'm going to run the same experiment 500 times and average the results together. I don't have access to the fluctuating quantities. I only have access to the mean quantities, because that's what you can measure. So this is taking these fluctuating quantities that I don't know what to do with and relating it to gradients of the mean velocity, which is something that I can deal with. So the mean velocity is something that I have a handle on. I can measure that. I can have a theory for that. This, I just showed you, I can't get a theory for this. I can't get a good first principles theory for that. That's the end. So we're at a place where we have to make some shit up. So what we're going to invent is some mixing viscosity. And our mixing viscosity, we're going to assume is going to go like some mixing length. And this is the knob that I make up. It's a knob on my simulation. I got to approximate this somehow. How do I do that? Well, we say, okay, how thick is the convection layer in the star? It's some fraction of that. Times some subgrid scale turbulent velocity. Here's the other thing that we're inventing. So then we've got to come up with a statement for the turbulent velocity. The turbulent velocity we're going to say is our length scale times the gradient of the mean velocity again. Okay, it feels like we're making the same dumb approximation twice, and we are. So that's all right. So what mixing length says is that the Reynolds stress, the average of the interactions of the fluctuating term. So this is all the stuff that's going on that's small. So that's all the things that are going on inside my little averaging box that I can't actually see because I'm averaging out of it. And in principle, that doesn't make anything change, but in practice, it's gonna. So this is gonna be, let's plug all of these things in together. It is just equal to the mixing length squared times gradients of the mean velocity squared. And the reason this is useful is because there's one knob, and it's just a scalar parameter that I get to decide. This is foundational and very important theory that goes into things like MESA and your other astrophysics codes that evolve stars. And it works well enough to get an answer that seems right and seems to reproduce stars properly. It seems to reproduce pipe flow properly. So it's a theory that has a lot of teeth in a lot of different areas. So the engineering models use this a lot. Astrophysics model uses this a lot. But it's clearly kind of nonsense because this is me. This is my knob. It's not self-consistently evolved from the rest of the equations. So it's a useful model, but it's also a deeply bullshit model. So the next thing you can do is direct numerical simulation. Direct numerical simulation. And that's basically this, but you incorporate the viscosity term and you make your grids really damn small so you're not losing too much from the subgrid model. That works fine. Another more sophisticated thing that you can do is called large eddy simulations. And what that entails is I'm gonna take all these equations, and I'm gonna skip the math here and just tell you about how it works. And I'm going to write an equation for K and epsilon, where epsilon is the dissipation of the turbulence at the small scale in the subgrid. So in the fluctuating terms, this is the dissipation. And kappa is the transfer of energy from the mean flow to the fluctuating flow. Does that make sense? I can write down equations for those, and then I can simulate them. But now I have two new variables. So now K and epsilon are new variables with new equations that I also have to deal with. And I've invented them, so we don't know if they're actually right, but they seem to work. So that's saying, okay, the Reynolds stress says that when I simulate this box and I break it into these little averages, there's crap going on in here that the averaging is missing because of the turbulence, because of the Reynolds stress. So we're going to have some transfer rate and some dissipation rate inside the box that will take care of all of the extra stuff. So there might be extra flow in this direction. There might be extra dissipation of the turbulence. So what I think that you're going to be on the hook for is really deriving the Reynolds stress and talking about what it means and what it does. I don't have enough homework. I don't know if I have enough time in homework problem slots to make you do any mixing length stuff, and I've already assigned the homework. So this stuff isn't stuff that you're going to be on the hook for, but the Reynolds stress is. Getting the Reynolds stress and knowing why it's a problem and what it says, yeah.
I guess this is not exactly an easy question to answer, but like how big relative to the rest of the numerical values would you say that the Reynolds stress is? Like, is it something very large, so like when we run models without Reynolds stress, it's just something that's very off, or like, is it relatively small, so it's just some small details we're trying to get correct?
That is a great question.
Oh.
So we don't know how big it is.
Well, it depends on the problem. It really depends on the problem. So if I have, when I simulate turbulence, I have a big box of gas, and I dump energy into it like crazy, and the mean flow is 0. So in all of this, all of my mean fluctuation, all of my mean flow is 0, and the only thing that I have is the fluctuating flow. So it totally dominates. It's absolutely the biggest thing in the signal. Or I do other simulations where I have a galaxy, and it is going around at 270 kilometers a second, and then I have turbulence at the 10 kilometers a second kind of size scale. So sometimes it's pretty subdominant. So that's a really good question. And it's a good question to ask now, but it's also a good question because that's the question that you got to ask when you're setting up a simulation, when you're setting up a numerical study or a theoretical study, is how bad is this, and what kind of approximations can I get away with? So in a star, it's really not that bad. The fluctuating terms are present and important, but you can get away with just mixing length, which is just my magic knob that I say, okay, there's some turbulence, boop, do your things. But for other flows, I can't. So, did you have a question? Okay. Yeah. You first.
Oh. So for mixing length, when you say it's a knob, do you mean you just figure out whatever makes it work, like with our calculator?
Yeah.
Okay.
Yeah, I just make up a number for a length. So this is like 10% of the star.
Okay.
And
yeah,
and that's a scalar that I pass in, and it's just a number.
And it works.
And it works reasonably well.
Okay.
Right? Because it's based on good intuition. Like I wrote it down real fast and kind of waved my hands past everything because really that's how it happened. But the intuition is reasonable. Like units wise, this should look something like that. Doing it this way is not right, but it's got to be related to the gradients of the mean velocity. It has to be. But for mixing length theory, it's just this is going to be 10 to the 7, and I'm done.
So like I understand that like that term comes from the fact that like turbulence in the fluid.
Uh-huh.
Like what's like the physical reason why there's like this quantity that is very unusual, or like we are unable to like really get to it.
Because Navier-Stokes is nonlinear. So because because of the v dot grad v term, because there's two v's there, when I try to expand it, that is the interaction, v dot grad v is the interaction of the velocity with itself. It's the velocity pushing around the velocity. And so because of that deep nonlinearity, that to know what's doing the pushing, you gotta know what's being pushed around. And to know what's getting pushed around, you gotta know what's doing the pushing. Because of that duality, because you have to know both of those things, when I try to do something smart and average things, out pops this Reynolds stress that says, you forgot the nonlinear term. So it all comes from the nonlinear part of the Navier-Stokes equation, which is why we try to get rid of it. Like, we spent a whole bunch of time linearizing it, because what linearizing it does is gets rid of this term. It turns this into just rho times grad v, or something like that. And then we can solve it. Once it's linear, you can solve it.
So if you linearize it, obviously you don't end up with the Reynolds stress.
That's right.
Okay.
Yeah, because when we linearize it, we throw out the prime terms, right? And this is two prime terms, so we throw it away.
Okay.
So the problem that happens when this becomes the size of the mean flow, when the thing that you're going to throw out is of the order or bigger than the mean flow, then you don't get to throw it out anymore. Cool. Does anybody have any other questions on any of this yet?
About the exam.
Oh, yeah.
What kind of exam is this? Like, are we gonna have like an equation sheet?
Oh,
or
yeah.
a calculator?
You won't
Like,
need
what's
a
the-
calculator. Yes, have an equation sheet. I'm kind of,
Like, yes, you will provide?
no,
Okay.
you can make one.
Okay.
So I forget, now I forget what I did last year,
Okay.
if I provided an equation sheet or not. But I always do for XGAL. And for this one, I think making an equation sheet is a really valuable process.
Yeah, it's like studying.
Yeah, I mean, because it takes, you gotta study all the stuff, and then you gotta go through all the stuff and distill it down to one 8.5 by 11 sheet paper.
Right.
And there's only two equations that we've really talked about in
Mhm.
here. There's continuity and Navier-Stokes, but then we take Navier-Stokes and we cut a part off, or we mash it together, so we get the momentum equation, or we get Euler's equation, or we get the internal energy equation. So there's really only two things to remember, and then what to do with them. But yeah, so go ahead and have a 1 8.5 by 11 both sides, however much you can cram on there. That's a valuable thing. And then the test is going to look like the homeworks for the most part. Like, I'm not going to throw you any major curveballs. My
Do you know
test.
how many questions already?
I don't.
Okay.
So, but that's why I ask you how long things take you.
Okay.
Um,
Okay.
Because I go through the homework questions and I say, well, okay, I think I've got an hour of actual time where you're sitting here working, right? That's kind of what I target, is a test that'll take you about an hour. And I put whatever is going to fit into that. I'm not quite that specific. It's really more shoot from the hip, but yeah.
Will homework 3 be graded before the exam?
I'm going to grade homework 3 today,
Okay.
like right now. And I'm going to try to grade homework 4 immediately after class on Tuesday, so you have that done too. And then on Tuesday, we'll talk about homework 4. And the solutions, I haven't put up the solutions. I'll put up the solutions to everything.
All homework.
I'll put up the first 3 right now, and then I'll put up the homework 4 right after class. So please give me homework 4 on time.
And if we got full credit on a question on the homework, we would expect similar on the test. Like, we wouldn't need any like more detail or less detail or.
Yeah, that's about right.
Okay.
Though, okay, so I'm a super soft grader. If I took points off, look at that.
Okay.
All right, so anywhere I took points off, go make sure you understand that. Even if I only took a half a point off, that's a thing that I want you to look at. And then some of the problems I didn't grade very carefully. Like the internal energy problem, I didn't grade real carefully. I just was like, you got most of the way there, you get credit. So a couple of problems I just gave you credit for, even though it wasn't perfect, but also I'm not gonna give you something that involved on the test because that's kind of cruel. Okay, yeah.
What's the fourth quiz?
Oh, okay, do you wanna see it real quick?
Sure.
Do you have a minute? Okay, so I've got the one analytic thing that we can say about turbulence, there are two things that we can say about turbulence that are really pretty robust. So the first is that v squared, the average of v squared, goes like the length to the 2/3. So, okay, let's be a little bit more explicit with this. I'm now going to call this the structure function, which is v of x minus v of x plus r to the p. So, okay, we had correlation functions before that was the product of the velocity at a point and the velocity at another point. This is now the difference of those 2 points. Otherwise, basically the same idea. So if this is squared, then I get a v1 plus v2 squared equals v1 squared. That's just the energy in the system. Plus v2 squared, which is the same quantity, plus v1, v2. This is the autocorrelation that we were talking about before. So this structure function and the autocorrelation function are super related. So we could say that if this is a 2, then I know this is 2/3. That's what this whole Kolmogorov derivation gets us, right? The cascade works because v squared goes like L to the 2/3. You can, and I will totally spare you, but if you want, I will put up the turbulence primer that goes through the derivation. I have only actually gone through the derivation myself twice because it's long and I don't really need it, but I've gone through it just to make sure I understand how it works. It's involved and kind of hairy. So from this, I'm going to call this SP, and that's SP equals of R equals this function where P, I'm changing this power P up here. So why is that? So when I average, if I average Q to some power, what this winds up doing is making you really aware of the rare fluctuations. So if you have a rare large fluctuation, when I raise everything to the 7th, the rare fluctuations dominate. So taking moments like this is a way to probe what the structure looks like. So we have this idea that the pth order structure function should go like L to the p over 3. And if you do it for p equals 2, you get a basically right answer that is basically backed up by experiments and all the theories and all the numerics. If you do it for 3, then you get the 3rd order structure function, and this is a big proportionality, so this is some constant in front, and we don't know what this constant is. If you do it for the 3rd order structure function, then you get minus 4/5 times L. Full stop. There's no proportionality. There's no extra constant that comes out. This is just an analytic result for the 3rd order structure function in a turbulent system. And this is one of the great successes of Kolmogorov. And then one of the great open questions is that as I increase p beyond 3, I get a number that's way less than what I should get. It does not do this for numbers bigger than 3. You get something that's much, much, much smaller. But this 4/5 is kind of a magical result where you do a little bit of math and it all comes out. You don't need to approximate anything or wave your hands. You just get a 4/5. So this is the 4/5 law. And it's important and it's interesting, but I'm not going to actually care about it any further than that. I just wanted to say 4/5 out loud to any of you who have a wind up going on and studying turbulence in the future. You at least know that the 4/5 law exists. I should look it up. Okay, that's it. Have a good rest of the day, and I'll see you guys Tuesday. Office hours. Does 2:30 to 3:30 work for you guys? On Monday?
Monday, 2:30 to 3:30?
Yeah.
Yeah, that can work.
Okay. I have flexibility, so I can do 2 to 3, 2 to 4, whatever. I'll aim for 2:30 to 3:30, and then if you need to stick around, I'll.
I need a charger.
Oh yeah, you need a charger. Let me turn the cord.